So hello and welcome back. Today we are learning about operational amplifiers. An operational amplifier is a voltage-controlled voltage source that can perform several mathematical operations such as multiplication, addition, subtraction, division, amplification, attenuation, filtering, low-pass filters, high-pass filters, etc. Here we have a non-inverting amplifier. And what you'll see here is that the positive terminal on the op amp is tied to the input voltage Vn. The negative terminal is tied to a 2K resistor that goes to ground, and a feedback resistor that connects 4 kilo ohms connects the output to the input. This is called the feedback resistor because it connects the output to the negative terminal, and this is called the input resistor. Output is where we measure the output. Notice also that we have two power supplies, positive 15 volts and negative 15 volts. An operational amplifier is in its linear region when the output is between positive and negative 15 volts. Outside of that region, we say that the op amp is in saturation or the nonlinear region. Note that an op amp must have power to work and that the output voltage can never exceed the value of the power supplies. So what we're going to find today is we're going to find the gain for our op amp, which is a ratio of the output voltage to the input voltage. And we're also going to find the output of the op amp for various inputs, where V out is the gain times Vn. So there are two ideal assumptions that we can make about an op amp when it has negative feedback. Negative feedback means that you have that resistor that ties the output to the negative terminal. And this is what we call negative feedback. So when that is true, our first ideal assumption is called the infinite input impedance, and that means the resistance seen looking into the op amp goes to infinity. And what that means is that the current into the negative and the current into the positive terminals on the op amp is 0 amps. Now this isn't really true, it's an assumption, but it's really a very small current. The other assumption we can make is called the virtual short condition, which means that the voltage at the positive terminal is equal to the voltage at the negative terminal. This is also an ideal assumption. They may not be exactly the same, but this is only true because of that RF resistor. So in order to solve this problem, we are going to use KCL. And what you should see here is when we do KCL, because V positive is equal to VIN, V negative is equal to VIN. And so then we're going to do KCL at VIN. So you're going to have VIN minus 0 over RI. That's the current this direction. Plus VIN minus V out over RF. That's the current this direction. And that equals 0. So when you solve that for the gain, you're going to see that V out over VN equals 1 plus RF over RI. So what this tells you is that this is a pure amplifier because the gain can never be less than 1. So the gain is 1 over RF plus RI. So for the circuit I have here, 1 plus 4 over 2 means that the gain for this non-inverting amplifier is 5. Since it's a non-inverting amplifier, what that means is that if you put in a positive value, you get out a positive value. If you put in a negative value, you get out a negative value, and you recognize it as non-inverting because the input voltage is at the positive terminal. So what that means is that if I put in Vn equals 2 volts, then V out is going to equal 5 times 2, which equals 10 volts. Or if I put in Vn equals negative 1.5 volts, then V out equals 5 times negative 1.5, which is negative 7.5 volts. So positive in, positive out, negative in, negative out. Now, what if I put in Vn equals 4 volts? So what you would be tempted to do is say, well, V out is going to have to equal 5 times 4, which is 20 volts. And what I will tell you is the answer is no. No, because the power supplies are at positive and negative 15 volts, that means that this op amp is in saturation. Because the op amp is in saturation, it can never exceed the power supplies for the output. So the output for this is actually at 15 volts. So if you make a sketch of what this would look like here, this would be Vn, this would be V out, and it's going to be a graph like this, where that graph has a slope of 5 until it gets to 3 and negative 3. At 3 and negative 3, 3 times 5 is 15. So this is going to be 15. And this is going to be negative 15. And then for any value that exceeds 3 or negative 3, it stays at 15 and negative 15. I hope you learned something today, and I hope you'll come back again. Stay STEM-tastic.